Let's begin. Thanks for joining. And today I'm going to cover in great detail recurrent neural networks and transformers. These form like the backbone of architectures that are used for language modeling and majority of natural language processing tasks. But before I do that, I also wanted to share a little bit more about our department, what we do, what we stand for, and so on. So we are a very interdisciplinary department where there is broadly two streams. One is computational science and other is computer and data systems. So like faculty colleagues and labs in the former apply computational methods to do, let's say, scientific research on mathematics, physics, chemistry, biology, and so on. Whereas computer and data systems involves research related to, let's say, databases, systems, computer vision, NLP, and so on. And we have a broad range of labs. So you can go here, look at all the people who are teaching and doing research here. Many of my faculty colleagues have had an excellent track record in doing high quality research and have a lot of students who are like really distinguished at this point of time. So you can check this out. I am sharing all these details to you because very soon, in about a week, there is an admission deadline that's coming up. So if people who want to enroll into IISc for, let's say, their PhD program or Masters by Research program or MTech by Research program, can check out this link, which is all about admissions. So this is the admission notice, and it gives you all the details about like who's eligible, how to apply, and so on. So there is a lot of detail here that you can go through if you're interested, but I'll share maybe a few key points. One is that if you are from a centrally funded technical institute, we have simplified the entry through that program. So let's say you have already gone to one of these 122 schools. So there is a huge list here. Okay, here I think. So there is a huge list here which includes, let's say, IITs, NITs, IIMs, IISers, and so on. So we have a list of about 122 universities or institutes where you don't have to necessarily sit for GATE and qualify GATE. You are eligible to apply if you were a bachelor's or a master's in any of these institutes, so long as you hold a GPA of 8 and above. And another, I think, key point is that if you already have a master's, you are eligible to apply through the master's or MTech qualified mode of entry. So you don't have to again like write GATE or any other exam to be eligible to apply. So these are things that people I talk to often don't know. So I thought I'll just share it with you. Yeah, so the deadline for the same is about a week from now, 23rd March. And IISc offers, as you may know, like one of the best trainings in the country to do research, to build your career, to upskill, and alumni from our institute and particularly our department have gone on to become faculty members in other universities, both in the US and India. Many of them are leading scientists at companies like DeepMind, Amazon, Adobe, and so forth. So I think this is a great opportunity if you're interested, and I'm happy to answer questions over the break if you want to know more about the program. Okay, so last time we were talking about neural networks and how they were initially biologically inspired. A neuron was like just something that took in a lot of signals, and based on the weight of all the signals it was activated. And we discussed how a perceptron was a computational model resembling the neuron. So if all the, like let's say these are the inputs, if the weighted combination of the inputs is greater than 0, then we say that this neuron is activated. Otherwise, no, the output is 0. So this is a perceptron. We looked at how a perceptron could model AND and OR functions or AND and OR gates. But we realized that it could not model XOR. Why? Because we realized that this boundary happens to be like a linear weighted sum. So it can only model linear functions, and XOR happens to be a non-linear decision boundary. Like you cannot draw a line here or here to separate this out. So, which was a problem. But we realized that you could potentially club a few of these perceptron units to build a XOR. So as you might have studied in the past, like a combination of AND and OR gate can be used to model XOR. Similarly, a combination of two perceptrons whose outputs are inputs to the third perceptron can be used to model XOR. So this was left as an exercise for you to decide what are these weights, right? I hope you got a chance to think about it. But I think you probably got an intuitive sense that this is possible. You can do it. Okay, so we were able to model XOR through just 3 perceptrons. So we got inspired and thought, like, if this is good enough, just 3 are good enough, like why not, why not, okay, 1 second. Okay, like why not scale this up? So we could potentially, instead of just having 3 perceptrons, we could potentially have multiple units or multiple perceptrons, and instead of having just 1 or 2 or 3 features, you could, let's say, have a large number of features. So here there are n0 plus 1 features. Oops. Right? All of them go into all the units. So there are, let's say, n1 plus n1 units, and this is a 2-layered feed forward network. So let's say this is just like a perceptron which accepts all these n0 plus 1 features and has a weight associated with them, and this weight, this like weighted sum of features determines the output of this. So this can also be, like, if you're comfortable with linear algebra, you could potentially also very simply write this as Wx. Instead of, like, this is, instead of just writing the equation for this, you are writing the equation for all of them in a matrix format. Any questions about this? Like, or is this clear enough? So last time we also saw that the output was determined by this sort of thresholding function. If it is greater than 0, then we said 1. If it is less than equal to 0, we said 0. So this is this, like, kind of like a thresholding function where till 0 the output is 0, and above 0 the output is 1. But you can imagine to have more complex non-linearities, more sophisticated non-linearities. So we talked about a few of them last time. One was ReLU. One of them was ReLU. 1 second. Okay, one of them was ReLU, which looked a little bit like this instead. So it was 0 all the way less than equal to 0, and y equal to x for x greater than equal to 0. So you can imagine there could be multiple such non-linearities. The only reason why we need a non-linearity here is otherwise multiple layers can be just written down as a linear function. So if you apply linear operations on a linear function, like if you keep multiplying that with another w, another w, another w, you can club all of that and write it as one matrix. So this model will not be able to model anything except linear functions if there was not a non-linearity here. So non-linearity is somewhat crucial.
Sir, one question here, like if that linear function of a linear, it becomes a linear, then in the case of the XOR, it was a non-linear decision function.
Yes. So in the case of XOR, we were using a perceptron. So perceptron is also, like, if we look here, just because of this definition, it is like, so the decision boundary is linear, right? Because it's a weighted sum of these, but the outputs go through a non-linearity. Like it is this is the output function, right, essentially. So if this is your x-axis, right, and this is, let's say, your y-axis. So this output is, let's say, let me draw the outputs with black. So your outputs are 1 and 0, right? So this is also non-linearity, but a simple kind of non-linearity, if you want to call it that. Right, so now when you club these here in this function, you are applying non-linearities here. H1 and H2 can be like this is like the output of it goes through this thresholding function, right? Okay. So last time we also saw that one could potentially train these models using backward propagation or backprop. So let's say if you have something like a loss function here, right? What was the loss function, anybody? Yeah?
Deviation from the most favorable.
Right. So loss function captures deviation from the expected output. There can be different forms of loss functions. One of them could be like, if you're predicting a real value, let's say, you could just say how far I am from that real value. Or you could have a mean squared error, or like you could, across examples, compute the squared distance from the expected value and take a mean. Similarly, there are lots of loss functions that you could use, but the idea is that loss captures how bad your model currently is. Initially, all the weights that I was talking about, all the W's will be random. So you will very likely misclassify a lot of examples, give gibberish outputs, and therefore incur a large loss, right? And now, so long as the loss is differentiable, we also discussed that you could apply a gradient based algorithm to slowly reduce your loss, right? So if loss is a function like this, right? So if loss is a function like this, and if you are here, you can take the tangent or the gradient here and slowly move downwards. This algorithm is called gradient descent. We talked about it a little bit in the past. So we also wrote down this equation. Right? This is just saying that I will update my W's in the negative direction of loss. So wherever my loss is decreasing, I will go there. Right? So this is also called the update step. But again, like all the libraries that you are anyway going to use in practice, like PyTorch, TensorFlow, JAX, they have what is called as an auto differentiation built in. So all these dl by dw will be computed for you. You don't have to analytically write it down. You don't have to do the math yourself. What it does is it actually applies this chain rule backwards. So slowly, like if you want to compute dl of dd, it will compute dl of de like this. Then it will compute de of dd, and then it will just multiply these two. This is like basic calculus. You might have gone through it at some point. It's called a chain rule. So if you want to compute a loss with respect to a variable, but there are multiple compositions or operations in the middle, this is how you back propagate your derivates. You had a question? Yeah.
So, what happens in case the function is not differentiable?
Yeah. So ReLU is, by the way, differentiable except at the point 0 where it is sub-differentiable. So at point 0, you just use the value of 0 as its gradient. For ReLU, that's not a concern. But in general, if the function is non-differentiable, then you cannot do gradient descent. So at least optimization through gradient descent is not possible, which is why for all neural networks we only use differentiable loss functions, differentiable operations. So it's a key requirement. Any more questions?
So when the ReLU becomes zero, like output becomes zero, so we are like when the neural network, the weights are randomly initialized,
Yeah.
then are we perpetually stuck at that particular
Yeah.
zero?
So great question. So so the question is like if you're using ReLU, a lot of times the values are zero. And if the values are zero, the gradient is also zero. So does that mean we are perpetually stuck there? So at least because of the way ReLU is defined, for those points you will not change if your loss is zero. So hopefully other weights are not at that state, which is why you randomly initialize, so not all values will actually be zero. So if let's say you initialize everything to zero in your W's, you will end up in that situation. Another reason why you don't want to initialize everything to zero is every single weight will have the same, there is no differentiation between weights, right? Every weight is acting the same way. You want different weights to start from different points so that they can potentially reach minimas, right? So again, like if you don't fully appreciate or understand this, you can treat this as a black box where if your loss is differentiable, PyTorch and most other libraries allow you to just call this function loss.backward. It will compute all the gradients for you. Similarly, if you have any optimizer like gradient descent or Adam or whatever optimizer you are using, let's say gradient descent, all you have to do is call optimizer.step and it will take this step for you. So it will keep updating these W's and you can track how your loss is going down. Okay. So this is all we studied last time. This is a slightly more complex network of some variables connected to other variables. So let's say you have A and L. So L, if you want to write dl upon dA, so this is like you will compute dl upon dE, dE upon dd, dE upon dA, and then dl upon dE will be just dl upon dE upon dE upon dA, right? This is just chain rule. You can go home and maybe like really practice and think about this, but this is yeah, question?
So you have many layers, then you always start from the closest layer and then keep moving backwards.
Yes. So basically the first step of backward, that's why it's called backward pass. So you start from the loss, you compute the function that's closest to the loss and compute the gradient with respect to that, and then one step back, another step back, another step back, and you multiply all those partial derivatives to compute the actual partial derivative that you need, dl upon dw. You can also maybe realize that if any of these are small, because of all the multiplication, some of these values can be very, very small. So this is also called as the vanishing gradients problem. You might have heard of it somewhere. Okay. So this is also called the vanishing gradients problem. This can happen if your neural networks are very, very deep. So that's why there is a big chain of multiplication, and one or two low values can really take your entire gradient to a very, very low value. And if your gradient itself is a very low value, then that means you're not updating much. Like if this is very, very low, either you need a bigger coefficient to multiply or you will not change much. So either your step size needs to be very high or you will not change much. Right, so this is like basics of deep learning, right? Okay. So we were looking at how you could potentially train a feed-forward network. So let's say if we were given a task of doing text classification. What is text classification? Text classification is like just assigning some topics or some classes to a piece of text. So you might have seen this in many, many cases. Let's say you're reading a newspaper or you're subscribed to some feed of the Hindu or the Indian Express. All of the news items get categorized into politics, sports, entertainment, and so on. Similarly, you might want to look at, let's say, product reviews, figure out how many of these are positive, how many are negative, and you want to, let's say, automatically categorize them. So, or let's say you have a company and people are discussing about this on Twitter, you want to just understand what is the sentiment of the audience or the users. So this is like very, very handy, useful problem. Shows up at multiple places. So let's say here, this is a review of let's say a dessert. It says dessert was great, and you want to classify this as positive, negative, or neutral, right? So what you could do is you could, on textual input, use a neural network, but first this input should be converted to a set of real numbers to be able to feed into a neural network. So let's say you compute some features or you extract some features from this piece of input text, right? Here let's say you have just 3 features. Feature number 1 says how much is your word count. Feature number 2 says how many positive words are there, and let's say you have a dictionary of positive words: great, awesome, amazing, fascinating, all that. So here great is 1, so your second feature is 1. And let's say this is a very simple pedagogical example, and the third feature is how many times you say no. No, it wasn't good, or no, I did not like it. So even though there are words like, good, presence of no is, let's say, important to capture. So if we just had a very simple network with very simple 3 features, we can take any input, convert these into 3 features, which are these 3 inputs, and they can then go into a neural network. So here let's say n is equal to 3, and it is going into dh number of units, like perceptron units, and outputs of all of those are further going into 3 units, and each of these units corresponds to 1 class. So 1 class will tell me how likely it is. So one neuron here will tell me how positive this is, 1 neuron will tell me how negative this is, and 1 neuron will tell me how neutral this is. Okay. Again, these will be raw real values to begin with. So this might be 9.1, this might be 8.4, this might be -10. You need to convert these into probabilities. We looked at a few things that you could use to convert these into probabilities last time. So like if you have just one value, so if you just have a scalar here, it is very simple to convert this into a probability. The very popular, commonly used function in deep learning to do that is sigmoid. You might have seen this somewhere. Sigmoid looks like this. So as you can see that as s tends to infinity, or as s becomes bigger, as s becomes bigger, this value starts to become smaller and smaller and smaller. So this is 1 upon e to the power s, right? So as s becomes very large, 1 upon e is smaller than 1. This number almost vanishes. So this value goes to 1, right? Which is also clear from this figure. Similarly, if s becomes negative infinity, then this becomes a very, very large positive value, e to the power plus infinity. And this whole denominator becomes very large, and 1 upon large denominator is close to 0. Right? Questions?
Yeah. So in the previous example, for sentiment analysis, you have 3 outputs, but you just need 1, right? Like if you say that output, like okay, how positive my review is.
Yeah.
Then if it's like if that probability after using sigmoid, you're getting like let's say it's 0.5, then it's like neutral. But if it's like 0, then it is not positive. So
Yeah.
why do you need 3? Like is there any?
Yeah. So that's a great question. So the question is, why do we need 3 outputs here? can we just say we will make one prediction? If it is greater than 0.5, we'll call it positive, less than 0.5, we'll call it negative, equal to 0.5, we'll call it neutral. You could potentially do it, but you have almost killed the neutral class here, because it has to be either exactly 0.5 or very, very close to 0.5. Another example could be, let's say you want to classify your reviews into highly positive, positive, neutral, negative, highly negative. So either you will have to divide the probability ranges into some, like, okay, 0.6 to 0.8 is positive but not highly positive. So either you need to do that, or it's better to have independent classes. Similarly, if you were, let's say, identifying whether this is sports, news, politics, then one is not enough, right? You can't say 0.7 of sports is politics, right? So it's generally acceptable to have multiple output units corresponding to a output class. Okay. Any more questions here?
This about the vanishing gradients problem you're talking about. So the goal of the system is to minimize the error gradient, right? So why would it be a problem that it reaches a very low value?
Yeah. So that's a great question. Why will, like, ultimately you want low loss or zero loss? Why is like, your question is, why is vanishing gradients a problem, or why does it happen?
And why is it a problem?
Why is it a problem? It's a problem because your gradients are astonishingly small. So either you need a lot of steps to improve on that function, and so in practice you could take infinite steps with an infinitely small gradient and get to a zero loss. But in practice that just doesn't work, right? Because you don't have that much time. Also, there are underflow issues often. So computers might not be able to also handle very low values. So typically a lot of these calculations are done in log space just to avoid those underflows. Any more questions? Questions there? A person with the red shirt? So if you have questions, please feel free to ask. Yeah. Okay. Got it. So yeah, we looked at a sigmoid function which can take an arbitrary value, let's say 3.1, and it can give me a probability. Because this function is between 0 and 1, probabilities are also between 0 and 1. So this function can be used to model a probability distribution. So whatever you get out here, you will typically apply a sigmoid of that output, right here. S1, sigmoid of, let's say, S2, sigmoid of S3, which is why you will get a probability output rather than some number. So you will get a probability of neutral, probability of negative, and probability of positive. Right? So that's one way to do it if you were to individually do this. Another way to do it, which is maybe better suited for multi-class problems, is what we call as a softmax. We looked at this also a little bit in the last class, where it is a normalization trick, where instead of just simply dividing by the sum, you exponentiate and divide by the exponentiated sum. So if you have a number like 162, you take an exponentiation of this and divide by the exponentiation of all the values. So e to the power 1 upon e to the power this is this value of 0.006. This converts a vector into a probability distribution. So as you can see, this sums to 1 by construction, by design. And this is also positive again by design. Exponentiations are never negative, so it's always positive, always between 0 and 1. And you can see that 6 here was the largest value. So the second index here is also the largest. So in some sense it is going to not change the maximum value. Like whatever was maximum in the first vector will also be the same index will be the maximum in the second transformed softmax output. So here a better thing would be to take out these three values and compute a softmax of this vector of 9.1, 8.4 and minus 10, and you will get three values, each summing to 1, sorry, not each summing to 1, in total summing to 1, each representing a probability corresponding to the first, second and third class, right? So you are able to take a sentence and do a task, you are able to take a sentence and do a task using a neural network, right? So we have kind of like made some progress here. You started with the sentence, you designed some features by hand, you wrote these things down, but after that you fed all these features to a neural network, you defined what is an error or what is a loss, and then the neural network did everything for you using back propagation, right? Question, yeah?
You computed softmax, then you realize that it is classified
Yes.
thing. That is when you calculate loss.
Yes, yes. So yeah, so I can maybe make this a bit more clear. Okay. So let's say if you were classifying something, you had a sentence, let's say desert was good, and you passed it through, let's say, a feed forward network, and now you got a probability distribution of, let's say, 0.1, 0.8, 0.1, but you realize that so this is corresponding to the positive class, neutral class and let's say negative class. So you realize that this was supposed to be positive in my input, in my data set this is a positive example, but my model is saying that this is the output, this is, my model is saying it's neutral, sorry. My model is saying that this is the y hat, this is the predicted output as per the model, right? So the model is saying neutral, but actually it is positive. So you should incur some loss, a high loss potentially, right? So now your loss function comes in here to define what, like your loss function will dictate how big your loss is. So in classification problems or in K-class classification problems, one common form of loss is called cross entropy loss. I mean, forget the correlation or forget the connection with entropy, but the loss is very, very simple. It just says this is negative of log of probability assigned by the model to the correct class. So here it will be probability that the model assigns to the positive class, right? So here you will realize that the loss actually becomes P of y equal to positive, which happens to be very small value. So it will be P of 0.1. So if you remember your log curve, so this is something like this, right? So but the region of interest is just this, because probabilities are never going to be greater than 1. So here, like, here so here as close you get to 0, you will incur a high negative loss, but that high negative is countered by this negative, so you will have a very positive, like if I were to draw the negative of log, this will be the curve, right? So because the value is 0.1, very close to 0, this will incur a very high loss. Ideally I want the model to take me very, very close to 1, so that I give this a very an exactly 0 loss. So just to recap this a bit, so you will typically apply loss which is negative log of likelihood that your model assigns to the correct output. So if it assigns a very high probability to the correct output, that means you are lying in this segment. That means you are lying in this segment, essentially. In this segment. Right? So you are incurring a low loss. But if it assigns a low probability, then you are operating in this segment, essentially, which is high loss. So your question was whether the loss is applied after computing probabilities. Yes. Okay.
Sigmoid is one of the famous functions. Like, and are there any function in with second best and why you?
So by default, most like 99.99% of the networks will do multi-class classification problems, and the final loss is softmax. Like the final operation before computing the loss is softmax, which will give you probabilities. There are some interesting variations of softmax. One of them is called sparse max, which will by design give you sparse probabilities. It will say 1 or 0 only rarely. It will not give you like 0.8, 0.9, 0.1. It will either say 1 or it will say 0. So it will give you sparse output. You can read about sparse max if you're interested. But this is again like used in special cases when you need sparsity. But softmax is by all means like the default.
What would be the bound of this like the loss functions? Is it only bounded between what would be the bound?
Right. What will be the bounds of the loss function? Great question. So at the lowest it can be 0. At the highest it can be plus infinity. Right?
When we are doing it between 0 and 1,
So the probabilities are between 0 and 1, which is why the negative log curve goes like this. So we are only interested in this segment of the curve because the input is a probability. So the domain of the input is 0 to 1.
so would it be meaningful if I say my machine is having this much more loss? I do not have to, I should change the architecture in case.
Great question. So if my loss is high, should I change my architecture? Not necessary. You have to find a way to make your loss come down. So some architectures are more, let's say, compute effective or might offer different properties. So we'll look at some more architectures other than feed forward networks.
So this is like for the calculating of the loss while training, we are actually assigning the label that the output should be this class. And then according to that class, we will calculate only the probability of the output of that.
Yes.
Then what will happen if we have like multiple labels?
Multiple classes. Okay, great. So excellent question. So this is a setup where only one class is correct. Sometimes you might have a multiple label output, like multiple choice questions with multiple correct answers. So this article could be both news and politics, but since it talks about Virat Kohli contesting elections, could even be sports, right? So there you need to change a little bit of this. There you need to make this into k binary class problems. So you need to, instead of saying pick one, you are going to say yes or no for first topic, yes or no for the second topic, yes or no for the third topic. So you should think of that as k binary classification problems. So for each topic you are deciding, is this correct or not correct. So similarly in that case you will apply a sigmoid for every class. So you will say that, okay, by 80% chance it is in news, 75% chance it is also politics. There you don't care about the probability summing up to 1 because multiple answers can be correct. Uh,
So how will the loss function look like
in that case, yeah, okay, perfect. So how will the loss function look like in that case? So let me maybe add one more page here. So let's say you have the same setup, but both positive and neutral are, let's say these are the correct classes. It's okay to say neutral, it's okay to say positive. So what you will do here is you will model these as three problems. One is whether am I getting this positive correctly, right? So you will have a sigmoid that tells you that okay, this is 0.9 positive, 0.1 this is not applicable here. Similarly for neutral it might say 0.8, 0.2, right, which is saying that there's a 80% chance that neutral is okay label for this, is an applicable label for this. Let's say for negative it says 0.7 it is an applicable label, 0.3 it's not an applicable label. So your loss will be, so what is the correct answers here? The correct answers here are 0.9, 0.8 and 0.3, right? You would want to say no here, this is not the label that applies, but these are the correct labels. So your loss will be negative of log of 0.9 plus negative of log of 0.8 plus negative of log of 0.3. So this is close to 1, so these are much smaller values than this thing, because here you actually messed up, right? You said that this is positive, neutral and negative, but your data said this is positive and neutral.
But why if you choose 0.3, you could also
Yeah, this is given by your model, this is not your choice.
you can penalize even further, right? Saying that it's horribly classified as a negative. So you can penalize even further by putting log 0.1 itself, right?
So you're saying change this to 0.1?
I'm saying that how to penalize it even further in terms of not saying it says point, it should be, yeah, from our data set it should be 0.1, but it says point. That itself.
In practice this works really well because this will drive the model to, like this is a very high value, it will make big updates in the model such that after some time you will get a 0.0001 here and a 0.999 whatever right here. So 0.55 also will, like it's just a function of how big your, like how poor, how badly wrong you are and how much should I punish the network. So if you were like if this model said 0.99, this is also the correct output, you will be like, how dare it, like this is absolutely wrong, I will have a very large loss. So this loss function basically has that mechanics inbuilt and it kind of like takes care of that for you. Having said that, nobody is stopping you to use only this loss. You can come up with your own loss function. Let's say your loss function could be, I will have a like you could have a loss function where let's say messing up with this class is a lot more severe. So missing detecting cancer is, let's say, a lot more severe than falsely detecting cancer. If I tell you that looks like you have cancer, you can at least go and get a second opinion. But if you had cancer and I said don't worry about it, everything's good, like it could cost you your life. So there might be cases where some classes are more important than others. So you might want to like have a coefficient that let's say says 100 times this. So if you are wrong on this class, I am going to penalize you 100 times more. If you missed detecting cancer, that's 100 times bigger sin than telling someone they had cancer when they did not. Right? Okay. So far we kind of have looked at options where we are manually extracting features. We are manually extracting features. Yeah, let's see. So here we decided that we are going to write 3 features. How many positive lexicons, how many words are there, and whether there is a no. Let's look at some automatic ways to do that. I mean, we don't want to be handcrafting these features, and if your features are not good enough, they're not expressive enough, then your model will not be good enough, right? It is a function of your features. If you're not, like if you miss the word amazing, then it will not detect that because you did not give that as a feature. So let's look at some better ways to do this automatically rather than relying on you. So one way to encode this is called one-hot encoding. So for every word in your vocabulary, let's say you have V vocabulary items. Let's say your vocabulary is 25,000. You're closer to Shashi Tharoor than me. So you can speak a lot of words. Now, for every word, you have a special index corresponding to that word. And let's say for amazing, that index is 1149. For great, let's say that index is 73. So by one-hot encoding, I mean is in a large vector, if the word is amazing, then only this will be positive, equal to 1. Everything else will be 0. So it's a one-hot vector. It's hot only when it corresponds to your index. So for amazing, 1149 index will be 1, everything else will be 0. Similarly, if I had a vector for great, only 73 will be 1, everything else will be 0. So this is a very simple way of representing words. It is also dumb because great and amazing are close, but if I look at their similarity in terms of cosine similarity, the dot product will be 0 because they are all different indexes. It's not capturing any of this notion of great and awesome and amazing are similar words. So it's not it's not the best way to encode vectors, but let's for now think that at least it's an automatic way. I don't have to craft features, every word has a particular index. Similarly, you could say that I have a bag of words. So to represent sentences, let's say if we go back and say if we want to represent this sentence, right, desert was good. So we'll say that this is nothing but a bag of words. So let's say if desert was index 99, this was index 107, this was index 445, then my vector will have ones corresponding to 99, 107, and let's say 445. So everything else will be 0 except these 3 values. So this is really like a bag of words. Like you are not capturing order. If the sentence was good was desert, you will still end up with the same representation.
What if the words are repeated?
If the words are repeated, great question. So in bag of words there are 2 forms. One is called a count vectorizer where you actually count. So if the word was desert was good, really good, so then one way to represent is I am going to take the good, it comes twice, so I am going to add. So I am just going to, instead of say bag of words, I am saying count of words. So both are acceptable. You could either say I only care about presence or absence, or you could say I care about counts. Different applications, one might be better suited than others, but that's perfectly legitimate way of encoding a sentence. 1 second. But is this clear? Like, is the bag of word representation clear? Question, yeah.
Desert that have different meanings, will they have same encoding? For example.
Yeah, good question. So different sentences that have similar meaning, will they have same encoding? Not as per this format, right? So if I said ice cream was great, desert and ice cream have no relation, great and good have no relation. They are just different indexes in this particular vocabulary.
A desert in itself means different things.
Yeah. So great question. So a word could be polysemous, like a remote could be a remote village or a computer remote. That is not taken into account here. The same remote is used, like there is only one identifier for that. Question?
Is the order of words also ignored?
It's ignored, yes. Order of words is also ignored here. This is a very simple way of encoding. We will come at better ways of encoding, but here it is ignored.
So, let's say you have a lot of data which keeps telling about desert only. What if the factor of desert itself gets recognized as a positive?
Yeah, great question. So the question is, let's say desert happened to frequently co-occur in positive things. Would that mean desert is positively associated? The answer is yes. So let's say if Shah Rukh Khan happens to do good acting and most of his films get positive reviews, then Shah Rukh Khan as a factor is a positive influence to the prediction, right? So the model does not know whether the word good is driving the prediction or Shah Rukh Khan is driving the prediction. It sees all of those as numbers essentially, right?
Data is a little lopsided.
Yeah. So which is where biases could also come. So let's say if you're doing, let's say, automated hiring, and everybody who said girls cricket team was not hired, then maybe the word girls might carry a very negative connotation. So you have to be very, very careful, because these are again systems that are purely associative. They look at numbers and they associate them with the class. Numbers that frequently co-occur with the particular class get associated with that class. So, yeah.
You can't treat the system by giving a lot more bias to certain words, not less bias.
Yeah, so those things can also be done, but one other simpler way is you augment your data, or you get a more representative data set. So if you happen to only interview very few, let's say, women candidates, and somehow they did not make the cut, rather than having a feature that women, like having the model assign a negative weight, you should interview more women so that you have a representative sample, right?
So, like this desert was a good. Can't we have this as a one-hot vector?
The whole thing as one-hot vector? Yeah, you could potentially, but for every 3 words there would be vocabulary cube possible combinations. So that space really blows up. So if I allowed every trigram to have a one-hot vector, then I will have to have v cube number of values here, which can be a lot.
How this will compare with that? I mean, of course, in space complexity, this is better.
Yeah.
But what about like why we are using this bag of how it is advantage?
So okay, so yes, on space, so it's not like just this is better on space. If you were allowing a v cube number of representations, right, like if each base unit was 3, then v cube for even a modest vocabulary of 10,000 becomes a billion. That's just a lot. That's just like practically not possible, infeasible, right? And the other issue is that their desert was great and desert was good will have a different index. Here at least you are sharing desert was between the two. So here the similarity, cosine similarity between desert was good and desert was great is non-zero because desert was is common.
In the same sentence, if a desert has different meanings,
Yeah.
we are using desert as a sweet and desert as a place where it's too hot.
Yeah.
So somewhere we are talking about positiveness
Yeah.
and somewhere we are talking about negativeness. What about the model we see? It is a positive thing or negative?
Yeah, great question. So model will not have the ability to conceive that this could have two meanings, right? It will always, like by design you are mapping it to one index. So there were older systems which would do what is called as word sense disambiguation first, and based on whichever sense of the word is being used, they will have a different identifier for it. So Apple the company was a different index, Apple the fruit was a different index. But that's not how we do, that's not how this representation works, and that's also not how, let's say, GPT works, right? But it was tried and done.
Instead of having real numbers here, what if we use complex numbers where we can at least represent a diagram at one instance?
So diagram also, I think the complexity, space complexity blows up.
No. Instead of the real numbers of 1 and things like that, can I make use of 1 plus j something? 1 plus j 0.
So basically you can use it, but if you have, let's say, a plus iota b, and if this can be v and this can be v, and all cross combinations are possible, then you are ending up with a similar problem. Right? Okay. So another form of representations is what is called as embeddings. You might have heard of word embeddings or embeddings. Those are like, I don't want to be in the business of giving this. I will just let a model create an embedding. So how it works is, let's say you have a one hot vector. Let's say this is for the word great. So this is let's say r cross v. Okay, so this is a one hot vector. Now you are saying that I will randomly initialize a large vocabulary cross d-dimensional embedding matrix. It's called an embedding matrix or a lookup matrix. Right? And this will be, let's say, random to begin with. I will multiply this with this embedding matrix. So V into V cross D, I can do that multiplication. I will get a d-dimensional output. But what this multiplication will essentially do is it will pick the third row for me. Is that clear? So if I multiply this, like if I multiply this, I get 4.3 and so on, right? So convince yourself that this is just a way to pull out a row from that matrix.
So this is like already there.
This is a new matrix called embedding matrix that you have initialized randomly now, but it will, like all other weights, be trained as a part of your neural network. So rather than you having to give representations, this model for the word great will have that representation 4.3 blah 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 to begin with, but that representation can be updated like all other weights, can be improved like all other weights, and by the end of neural network training you will have a much more refined vector, refined representation for the word great.
How do we choose the dimensions before itself?
Yeah, so the dimensions is a hyperparameter. So you could start with something like 300, 600, 1200. This is just a hyperparameter. You try different options and see which one gives you the best performance. Actually, in practice, the question really is, what is the biggest dimension I can which is the biggest dimension I can hold in my GPU memory so as to not go out of memory. I think there was a question on streaming. Do we have 3 vectors? Hello. Can you show me the question? So there is a question from Saurabh. Can you do we have 3 vectors of 1 vector? Can you clarify, Saurabh? What do you mean by 3 vectors of 1 vector? So essentially, for a word like great, you will pull out this row which is of d dimensions. So every row will have, so every word will have ultimately a d-dimensional vector.
So whenever, even though you randomly initialize this embedding matrix, and you said that you will train a neural network, but you need supervised data to learn this.
Yeah.
But if you don't know what embeddings are, to train the neural network, how will the neural network learn this random weights?
Yeah. So this will become clear when I show you the network and show you the task that I am using to train it. So we were talking in the very first class about language models, which is I think what the course is about. So if we were to do language modeling, which is the task of predicting the next word. So let's say here I am looking at these 3 words for all the, let's say the correct answer is for all the confusion, right? Or for all the drama. So let's say that is the next word that is supposed to come here, right? So you will look at, let's say, the last 3 words. Build, let's say this is 35 index, this is 992 index, this is 451 index. You will get that row from that particular matrix that I showed you, and you will get an embedding vector for these 3 words. Now these 3 words will be inputs to a lot of perceptron or neural units, which will further be connected to another layer to give you a vocabulary number of classes. Like we said, positive, negative, neutral, here every word could be a next possible candidate, right? Because anything could come here and we want the system to be able to generate every possible word. So you have a vocabulary class as your output. So language modeling is being modeled as a K class problem where K is your vocabulary. And now if in the data the answer was confusion, your loss will become what? Can people tell me what will your loss be? Minus log of probability of predicting confusion, right? So if the model did not say confusion, you will penalize it, you will update it, including this embedding vector and matrix, right? So including this matrix here will be updated if you are not getting a good enough loss. Like everything by default will be updated. So just like you back propagate all the weights of the network, even this matrix will be updated. Now the question is, where do you get all this data from to do this much updating, right? I mean, this seems like too good to be true. But remember that your internet is full of text. There are trillions of tokens which you can pose as next word prediction problems. So for every 4th word in your internet, or for every word rather in your internet, you can say, looking at the last 3 words, I'm going to make a prediction. So if there are 20 trillion tokens on the internet, you have 20 trillion data points. So this is also called as self-supervision. So no human being gave you annotations of good, bad, negative, positive. By the art of writing, you got this data for free. Because somebody wrote their poems, their reviews, their rants online, you can now perform this task. You can now update your neural network using the data that is out there in public domain.
So, like, what is the lower bound on the D? Because if the size of the vocabulary is 50,000, I can fit all the points within a circle. As I move to the 3 dimensions, then I can fit all the points within a volume of a sphere. So, what is exactly the lower bound on the D? Is it accuracy or?
So, okay, great question. So, how should we think about D? So, if D is 1 dimension, then every word is getting represented as a number, which is not very far away from here, right? This is already a number. So it really depends on how much knowledge about a word you want to encode. Higher is the better option because you want to capture lots of things about words. So to give you an example, a word like knife, it can be used to murder someone, it can be used to cut a vegetable. It can also be a symbol of, let's say, protection or safeguarding. So many things can be associated with the word knife. Like, a lot of things come to your mind when you think of knife. So depending upon how powerful your model is, your D will be large. So let's say GPT, Ds are close to tens of thousands. But if you think of a theoretical lower bound, just to identify and distinguish a word great from any other word, you just need 1 scalar essentially. Okay.
So embedding, like this embedding layer, can it be learned separately from the whole layer?
Yeah, great question. Can embedding layer be learned separately from the neural network? It is possible to learn embeddings through other mechanism and fix that embedding. So that is also possible, but these days it's rarely done. So there was a time between 2015 and 2018 where people had found out a way to train word vectors. The 2 popular options back then were word2vec and glove, which people had found another way to train, and they were very good vectors. So people used to load these as word2vec vectors. So that matrix was word2vec, and people would typically not change that, and everything after that will be tunable. But that is not a common practice anymore because we have better compute and access to bigger data sets now. So we don't have to do that. Okay, I understand. So I was talking about, so the question I think Saurabh really wanted to ask was something different. So here we were talking about, so the question is, when we're talking about one-hot vectors for a sentence like desert was good, are we talking about 3 vectors or is this 1 vector? So this is 1 vector, and this representation is no longer one-hot encoding. It is called bag of words, and each one corresponding to its own, like all the words, all the active members of this vector correspond to the word, correspond to 1 word in the sentence. So 1 word corresponds to, let's say, desert, 1 to was, this is 107, sorry, and 1 to good.
So when in the diagram next, we represented all the words as vectors and performed vector algebra. Now the last stage where you got a vector, how did that exactly get converted into a class?
Okay, great question. So at the end, I got a R to the V dimensional output because I have these V number of output units. I will perform a softmax to convert that into a vocabulary sized probability distribution.
No, so each word has its own vector. So because it's all vector operations.
Yes,
after that.
yes. So that is at a feature level. Once this has been fed at different hidden units, then output of every hidden unit goes to every unit in this layer. So the role of words is kind of like encapsulated here.
What does the output look like? Is it going to be another vector?
It's going to be another vector of size vocabulary,
And then
which contains the probability of producing every word corresponding to that index. So let's say the value of 35 is 0.02. The interpretation is that the probability that this network assigns to predicting for after this is 2%.
When we are doing machine translation, so does that mean our vocabulary has to include the Japanese, French, German?
Yeah, we will come to machine translation in the next after break session. I'll explain that please.
So when you do a hot encoding, basically out of whole V points, you have only 1 point. I mean that you repeat for every word, right? So that row you repeat for every word if I want to predict that. So is it not too much of computation just to give importance to that one word and remaining zeros, and because in terms of computations,
Yeah. So I think so. This is a matrix multiplication, right?
Yeah.
So if this is an x, this is an e. This is just one matrix multiplication. And if you have, let's say, 10 words, right? So let's say x is a matrix rather than a vector. Then you can also directly do this matrix multiplication and look up 10 words in one go using a matrix multiplication. And
but end of the day, it has to compute that V into V again, because that
so at the end of the day, yes, it has to compute a V dimensional output. So softmax, this last step is definitely a bottleneck. It takes one of the most compute intensive steps.
In the embedding matrix, would it be wise if we have some handcrafted feature
Yes.
or something else?
So would it be wise if we had some handcrafted features in the embedding matrix? If you have strong intuition or strong requirements, you can have that. It is not prohibited, but that's not typically the normal practice.
It's just about the question about like these numbers are like V cross V is D cross V.
Okay, so the numbers are not matching. Okay, so this part is clear, right? So there are 3 words that we are looking at. So we have 3 one-hot vectors. Now you have this matrix that is, I was showing you a V cross V matrix, but this is a D cross V matrix. They are multiplying it. They are doing e to the power x rather than x, ex rather than xe. But you will get 3 d-dimensional vectors. Sorry. Okay, so you will get 3 d-dimensional vectors. Is that clear?
Yes. Separate 3-dimensional D.
Yeah. So this vector is for the word for. This is for the word all. This is for the word the.
So this is this network will always take 3 words.
Yes, yes. So this is a 3-gram feed forward neural network. It will always take last 3 words. It cannot look before that, and it will always predict the 4th word essentially. So instead of like having handcrafted feature like desert, good, bad, you are learning features as a part of this network, and it's a feed forward network.
So at the end, when the embedding matrix is created, will it also take into consideration similar words which are being said?
Yeah, it's a great question. So because it so happens that words like the movie was great, the film was great, similar outputs are expected when movie and film occur in your context. They will, as a virtue of training, happen to have similar embeddings.
So
So it's not like you are not deliberately forcing that, you are not designing for it, but that naturally happens because that is easier for optimization.
If I take the cosine similarity, will I get a number?
Yeah, you will get you will find that film and movie are maybe closer than film and Apple.
But what if we extrapolate that to sentences? So for example, I love apples very much and I hate apples very much.
Yeah.
Only one word is different.
Yeah.
So
We don't talk about sentence embeddings here so much, but I'll come to a more elaborate architecture where we will talk about that and I can explain that in a bit more detail. So this paper, this diagram and this architecture was introduced by Yoshua Bengio and some of his students. I think in this landmark paper in 2003 or somewhere between 2003 to 2007. This is a point of time when nobody was seriously doing neural networks and wasn't seriously applying it to the task of language modeling. And they had shown that this is quite competitive in terms of performance. But I think only in 2013-14 when people started scaling these systems up, it became very apparent that this was the way to go. Yeah, so this is not very far away in like broader history of computer science. So we are like 20 years from there.
Does this vector, using this vector, solve the issue that you showed the example of apple being a fruit? And
No, it does not. Right, because yeah, like we are giving the same index to the word apple, fruit, and company. So yeah.
No, but when you see the embeddings, wouldn't it be closer in one dimension and a little farther in another dimension? When you actually visualize it, it would be closer.
So what actually, so in like these days and even for this model, we never give a different ID for the fruit and for the company. But the model is expressive enough. The model has seen apple in multiple contexts, some of which are fruit related, some of which are company related. So the model is able to assign some components of this d-dimensional array to serve as a fruit, some components to serve as a software company. So that somehow automatically happens because the model is forced to produce the correct output again and again. So when it sees the CEO of Apple was, like those parts of that embedding are used compared to like when you're saying that I bought bananas and apples. Okay, so let me move forward. I will take more questions. But one thing you are noticing is that we can't do more than 3 or more than fixed numbers. So it's a k-gram language model. It has to have a fixed window. So ideally we want to go to a state where we can consume multiple sequences of variable length, right? So this one has a lot of problems. One is it cannot capture long-term dependency like we were talking about in grams, right? So if it is 3-4 gram, it can only do that. So this is where we bring up recurrent neural networks. So time flows, like language also flows, so there is like a temporal component of it, right? You want to handle variable length sequences. So this is a very, very simple architecture. It is slightly different from a feed-forward network. The special thing about it is that at time step t, it consumes output of t minus 1, which is why the word recurrent. So basically it eats up its own output, right? So what does that even mean? Like if you were to unroll this, this is what it looks like. So this is the same network, same A with the same weights. So this A is not different from this A, but let's say you passed the embedding of first word, you get some output here, which is how to get that output I will explain later, but that output is now the input of the second RNN. It is the same RNN as the first RNN, but it is the input to the RNN at the time step 2. Similarly, at this time step, the output from the previous time step is an input. So as you can imagine, by unrolling this, you can run this for as many number of steps as there are words in your sequence. So if you had only 3 words, this will be your network. If you had 4 words, you can use you can add 1 more. Right?
The operation of A is same in every case?
Yes. So the network A is the same. I will define what that is and what operations it actually does.
Also,
Question?
what will you do if you just if you have let's say if you design this for 10 inputs but only 2 or 3 inputs are...
Yeah, it will still work. Let me explain how this works. So it can handle variable length sequences. So these are the 2 operations that a simple RNN does. It is also called as L1 RNN because this is the person who introduced it. So it does 2 things. So it has 2 inputs. The XT that we were talking about here, right? And the output, the hidden output from T minus 1. So this is the H0 here, the same H0 here, same H1 here, same H1 here. So the output that we are going to produce is this input to the third RNN here, RNN at time step 3 here, right? So it will take at time step T, it will have 2 inputs, XT and HT minus 1. What is XT? XT is the row or the embedding that you have pulled out for the Tth word. So if the third word is good, it is that row in that embedding matrix, that vector. Okay? What is H2 here is the output of the RNN at time step 2. So it does very simple things. It basically multiplies this with another D cross. Let's say if XT is R to the power D, W is, let's say, R to the power D cross D. Let's just simplify this. So it just does a weighted multiplication. Similarly, HT minus 1 is also transformed by another weight matrix. So these weight matrix are telling you how you should weight every single feature that is there in XT and HT minus 1. How you should see the third dimension versus the fourth dimension versus the ninth dimension. So the ninth weight corresponding to the ninth dimension is closer to 0. That means it will have less influence in the final output, which is how you should implement, how you should think of this products. And this G and F are just non-linearities. You don't want this to be a fully linear network. So you have non-linearity. G and F are just simple functions that are non-linear. You can think of them as ReLU functions or tanh functions, right? These are just very simple functions. So RNN is nothing but it takes 2 inputs, XT and HT minus 1, transforms are using matrix U and W respectively, adds them and takes a non-linearity. Now this gives you an HT. Before you finally output it, you also, let's say, want to project it. Why is this needed? Let's say your dimension is 300 but you want to output a word in V dimensional space. You will have to project it to a V dimensional space. If you just want to say whether every word is positive or negative in a given context, you want to project it in 2 dimensional space. So this is like for projecting to K final classes. So let's say if you want to produce words, then this will be D cross. So this is very simple. If you want to unroll this, this is what it looks like, right? So this is the operation with x1 and h0, right? The output of this is transformed through v and goes to x2, and this is the unrolled version of that.
We are actually learning the U, V and W.
Yes. So the parameters of this model are U, W and V. There is also an embedding matrix here because that's what is giving you the embedding, which I have not shown, but that is also there. So these are all the four unknown matrices that you will learn as a part of this network.
This is like the one is there and this is
Yeah, great question. So this V is not different from this V. This W is not different from this W. It's the same matrix, which is why you can apply it for any number of times. If there was a V1, V2, V3, then I'll have to tell you how many V's are there, which will predetermine how many words can you consume.
So in that case, like when we are back propagating, it has to remember.
Yeah. So we'll look at how to back propagate this, but at least I want you to think about this, that this can consume a variable length sequence just by virtue of unrolling an array.
So if how is W saved for all the x's?
That is your choice. You are just saying that I'm going to use the same W. You are doing this computation yourself, right? So in some sense you are writing this function in a loop for t equal to 0 to n. You are going to keep applying the same function with the same u and w. The only things that will change are x and h, because your inputs are different and as a result your h's are different.
When you say output, we just mean like the coordinate distribution across each one of the
Yeah. So there are two notions of output. One is called the hidden state. People sometimes also call this as an output. But technically the output is when you've transformed into the vocabulary space, if you're making a vocabulary space output. Like if you're predicting words, if you're predicting sentiment of 5 category, then the output will be 5.
So the hidden output, what is that? Is that
So hidden output is this thing that is passing along across time, and that is the same thing that is later also projected to, let's say, give you a vocabulary dimension output.
so we haven't yet discussed how the hidden output looks like.
So if the X is clear, right, if X is a row of that embedding matrix, then hidden dimension is given by this formula. If you just look at, sorry, I think butchered it, but this is the formula, right? This formula determines what H is. Okay?
So the U thing will be having the context in some sense.
So basically all that is to be remembered about what is important in your context should be relayed here. So it will come through H, not U. So like U, W are parameters that you will learn, which will also tell you how to treat X and H, which will of course be a function of the context.
So in the unrolled version of this,
Yeah.
So what we can just see is that U is being passed out.
No, U is not being passed out. U is the same U that is being applied here. So basically, so H is the output here, H1 is the output here, which is transformed by U. So H is essentially being relayed, but it is transformed by U. So last question, and I'll stop and take a break, but we'll come back and show this.
How will you select the value of HC?
H0, great question. So maybe for now you can think this is all zeros. So all zeros will not change the first part. So when you're starting this will have a 0 contribution. But H1 will have some meaningful value based on X0. Okay? So H0 is 0 to initialize. Okay? So we'll come back from this and we will go from here. Okay? So we'll take a break. Quickly revisit the RNNs. These were the two equations we were looking into. Right, so these were the two equations we were interested in. So it's a very simple formula. You just transform your xt and ht minus 1. These are the inputs at time step t, and they're transformed by w and u matrix respectively. And then you take a nonlinearity which gives you the hidden output at that time step ht. Ht can be used to get you the output you deserve or you want. So you can transform ht into whatever dimensional space you want through a matrix multiplication, and let's say f could be softmax if you want to convert them ultimately to probabilities. F could be softmax, right? So all of that is possible, and like if you are maybe a bit like if this notation is not very comfortable to you, how these matrices are being multiplied, I would say write it down on a piece of paper, open these terms, and you will, I think, become more familiar. So it is a very common operation in deep learning to transform a vector into, let's say, a different space, transform it back into another space, apply a non-linearity. So this is something I think being comfortable with is worth it.
So if I reduce the dimensions of the ht very much, so are we going to lose some information when we pass from point?
Yeah. So I mean this dimension d of hd, right? It basically essentially controls how much space. So the question is, if we were to reduce the space or the dimensions of ht, are we going to lose any information? The answer is yes. Like if you can imagine that if it's only a one-dimensional number, the total number of bytes that it can encode is very less, right? Similarly, if you had a much larger space, you can encode more information that might help. Question?
For example, if you go to, let's take h of 100, right? Obviously we'll start from 0 and go to 199. So as we approach to the h of 100 or to that 100 instance, since we apply this lot of non-linearity, so what we use the context what we wanted to achieve in the first place?
Yeah, so that's a really great question. The question is, if we keep applying this to, let's say, h1, h2, all the way till h100, will h100 have any information about h1 at all? Will we lose that information? The answer is yes, quite likely we will not be able to retain information for these many time steps. In practice, like RNNs are like 7 to 10 steps of information can be, let's say, reasonably encoded. But being able to attend to information a long while ago or a few time steps ago is very challenging, because this is sequential in nature. It goes left to right, one step at a time. So that is an inherent challenge. So one challenge is it's sequential. Second is longer contexts are harder to capture. I mean, this is much longer than a typical n-gram, right? N-grams are 3 or 4. If you go to much higher n-grams, then there are like severe sparsity and space constraints. This can easily model words that are, let's say, 4 or 5 time steps away. But by longer, I mean, let's say 10 plus. Contexts are hard, right? Hard to capture. So these are the two major weaknesses that transformers, which we will study in some time, solve. So I'm glad that people are already able to identify these as limitations. But let's, like, before we go to transformers, let's look at a few more properties of RNNs. So one thing is like, okay, we've introduced RNNs, how do we use them for language modeling? This is how we would do that. So we typically start with, let's say, whatever words we have, we get an embedding for them. How do we get an embedding? We pull the row corresponding to the word we have. So if the word says 441, we pull the 441st row out of that embedding matrix. It's also called as a lookup operation. Now you have an embedding, this becomes your x1, x2, x3 and so on, right? This is your h1, h2 and so on, right? Now this v will transform at a vocabulary space, will transform the hidden dimensional space to a vocabulary sized space. So you will produce a softmax over vocabulary. It gives you the probability of which word could come next. Again, the task is the same, language modeling, which word can come next. So here the loss again is also very, very familiar. We have done this. It is negative log of probability of predicting long. If the next word is long, we want to predict that, right? So if we started for this, so long, if long is supposed to come after so, we predict long. So the probability, so it's log of p of long. Y of long is just another way of saying what is the probability of long. Question?
Like why we are not considering the given, the first word was so and then we are getting
so is the first word, so there is no previous context here. But when we are predicting the second output, both so and long are being factored in. So long is directly an input as x2, but the hidden state after consuming so is also an input to this, right?
So in the loss also we will consider that only, like
So the loss will just be negative of log of probability of and, but remember that to come to this loss value, you are using information about the word so, because it is being passed on through this hidden state. So let's say if something about the embedding of so is not right, you will update that also based on the loss that you've incurred at time step 2. So if you are doing backward propagation, the loss that you are incurring here will go here as well as will go here, right? Because it is a function of this as well, right? The h1 is a function of x1. Output of time step 2 is a function of h1. So this is a bit more complex than the small computational graphs I was showing you where E was a function of D and A. But you can extend this mentally in a way that everything is being used to compute that output. So it's a function of all those inputs, and hence updates will touch all those things, right? Updates due to loss of log probability of and will impact even the embeddings x1. Question?
How would the gradient descent look like in this case?
How would the gradient descent look like in this case? Exactly the same as it looked like in every other case. You will have to compute d of log loss. So loss is negative of log probability of and now you will see how does that probability change with respect to changes in embeddings of 1, right? So if this value was 0.981, you will see, what does this partial gradient tell you? It says that if the value was slightly different, how would my loss change, right? So if the loss is positive, if increasing this means you incur a more loss, then you will rather decrease this value. That is what gradient descent does.
So let's say you go to the next step, then you have to go all the way back.
Yeah. So your total loss is a average of loss of first term, second term, third term, fourth term, fifth term. So this is written here. 1 upon t loss at every time step. So again, like if you imagine or think about each and every term, it might become quite tedious, but this entire loss is a function of a lot of inputs here. Good news is that PyTorch will take care of all of this for you. You don't have to analytically or mathematically compute gradients by yourself. PyTorch does that for you. How come it's so easy? Internally, it's a computational graph. Like it's complicated operations, but each operation can be mapped to simple operations internally in machine code, and it just has to do backward propagation. Right?
Wouldn't the gradient, the gradients vanish faster?
Yeah. So gradients vanish here. It's a problem with many, like let's say whatever loss is coming from here, it has to go through a lot of steps. There's a lot of multiplication that happens on the way. It can happen very well that some of these gradients become arbitrarily small. So it's a common problem to observe. So there are some advanced recurrent neural networks, like one of them is called long short term memory, LSTMs. They have a special gating mechanism to kind of avoid some of that problem, but they're also not free of vanishing gradients. It is a problem. So transformers happen to be much better at it because of some properties which I will explain in some time.
So what if I take the hidden state of the first one and connect it directly to the output?
Yeah. So you can build a slightly different architecture where instead of saying H1 like my current recurrent neural network is contingent on the past hidden state, you can make a choice that it will be contingent on the past 2 hidden states. That is also possible. But you might be tempted to then do it for past 3, past 4. So it becomes a bit arbitrary, but at least people have used what idea you are suggesting in. So this is like from time t to time step, let's say 100. But people have used this idea in depth. So if you have 100 layers, people typically will connect the output of the first layer directly to the 5th layer. So these are called as highway connections or skip connections. This is exactly meant to, it's exactly using the idea that you just suggested to be able to get rid of this vanishing gradients problem, so that there is a direct mechanism for the gradients to flow back. So this has nothing, so the question is, can it be applied to the unsupervised part? So this has nothing to do with unsupervised. All of this requires supervision, just that this supervision is coming for free because we are using the next word prediction as a signal, right? We are not getting people to annotate stuff for us. It's already English written text that we are using. Yeah, the highway connections or skip connections are not dependent on the nature of supervision. Yeah.
So is this a reason that why we are not using the prior probability of like in the p and we are not using p and of long, because given that long was the previous one and then we are getting and that probability will get reduced. So because of the architecture of RNN, we are only using the probability of and.
Yeah. So the question is, like, at time step 2, why are we using in the loss only the probability of and? Why not probability of long and? Probability of and given long. So we are using the probability of and given so long because they are inputs to the network. They are like, it's like we are conditioning on this x1 and x2. So RNNs give you probability distributions conditioned on the text. If you change your text, the probability distribution will change. So the and that you are seeing is conditioned on so and long.
Sorry, I mean in the loss function.
In the loss function, the probability of, let's say you made a terrible error of predicting long. So you have already punished the network for it, right, in the first step. You don't need to do it again in the second time step. So there are multiple ways to actually go about training this. One approach is that whatever the network has generated, I will use that as my second input. Okay? Another approach is I will spoon feed. I will give the correct input regardless of whether the model has produced the correct output or not in the previous time steps. So the spoon feeding approach is called teacher forcing. You can imagine why. So that is what is typically done, especially during the start of the training. At the start of the training, the models are quite random. They are producing random output. You don't want to be taking random output as your input. So as models are trained to some degree, you then start to move to the case where you are reusing the model output as input. Like you can let's say initially you said, so thanks, right? So let's say your prediction was thanks. You have punished the model, but the model prediction is still thanks. So the first option is I will use thanks as my x2. But in your input, the sequence is so long and thanks. So teacher forcing mechanism will say that, okay, use long. It's okay if the student has made a mistake, I will spoon feed. At the same time, when you are generating text, let's say when you are using this model to generate new input that you have not seen, you don't have that luxury of spoon feeding. You have to make your students really like work in the wild, right? So whatever they generate, they will consume that. Question?
So if because of for it changed the W's and all the other values from that.
Yes.
Now do we have to calculate new laws for again long and times and all of those, because that can have impact on the next word association.
Okay. So you're saying because of mispredicting for, I already updated some of these parameters which may have changed the previous predictions. So should I account for that? That's a great question. So in one cycle, first of all, in many networks and for many examples, you will go over your examples multiple times. So there is multiple epochs of training. Aggregate and average your loss. So the updates to, let's say, your embedding for so is determined partly by the loss from long, but partly also by loss for for. Whatever is the net averaged loss will essentially be updated. So for is impacting so, but that operation happens once. So you take the average once and update. You don't think that like, yeah, like, I mean, you update and then you come back to that example later.
And you come back to it later and then you start again from so.
Yes, exactly. So once you're done, you come back and redo this essentially. Yeah. Okay. Great. So yeah, okay, so this is now clear how RNNs are being used for language modeling. You know how they're being trained, you know the loss, you know how they're being like once you have a probability distribution, you can either take the maximum token which has the highest probability and use that, or you could say that if the probability is 0.4, 0.3, 0.2, 0.1, I will sample based on that probability. So if a token has a probability of 0.2, it will be sampled 20% of the times. So both approaches for generation are okay. These are called decoding or sampling strategies. The first one is you pick the maximum. It's called greedy decoding. The second one is you sample. It's called multinomial sampling. Okay. So when you are generating, as I was saying, whatever is predicted has to be consumed. There is no other option. You don't know the future. Similarly, you need not predict words. You can predict something else. So there is a classic problem of sequence labeling. Let's say you want to label a sequence, whether it is a noun phrase, a modifier, a verb, a determiner, a noun. This is sometimes useful whether, let's say, you want to know what verbs are used in a resume. People say that you should use bold active verbs. Or you could also say that I want to label my sequence in such a way that I'm able to extract named entities. So people's names might be labeled as begin of name, intermediate of name, end of name. So these are standard tagging tasks. But the point that I'm trying to make here is that you need not use an RNN for language modeling. You can use it for sequence labeling. Any kind of labels are okay. Okay. So you can also, by the way, use an RNN for classification. So you are not necessarily outputting or using the outputs at every time step, just that the last output HN, which supposedly has all the information because of the recurrence relation, has, let's say, all the information about the sentence, and now you use this as a features for a feed forward network. So similarly, like you were working with this sentence like desert is good or desert was great, you can have that as your input, run an RNN on that input, use the last state as features for your feed forward neural network. So if you go back to this example that we saw earlier, right, instead of we making features, you can potentially use a RNN to give you the final hidden state after consuming this sentence. Now this also does not run into the problem of fixed features or does not run into the problem of having to either create a list of features yourself or relying on, let's say, a fixed window. It can dynamically consume as many words are there in your review, which is, I think, the biggest advantage of a RNN. Okay, so RNNs can do sequence classification. It can, let's say, do sentiment analysis. It can do topic classification.
In RNNs for generating sequence, what is the target?
This is not training. It's like you're just using the model to give you new output after you've trained it. Okay, is that clear?
What about for classification?
Yeah, for classification here also you will have a loss based on whether your class output was correct or incorrect, and you will train it, but after you have trained it, you can pass a brand new movie review and ask the model to make a prediction.
What is the output of the RNN that is going?
So like you were predicting earlier in vocabulary space, here you will predict in, let's say, 5-dimensional space. So this space could mean highly positive, positive, neutral, negative, highly negative. So if these are your 5 classes, your output from this feed forward network will be a 5-class output. Question, yeah?
Can we take this instead of the last hidden state? Can we take it like at around regular steps, like 5 or 7 or like?
Yeah, you can take here, but this. So the question is, can I, instead of going all the way till the end, can I take intermediate outputs and do sequence classification? Yes. So you can do. So there are approaches. So it's called pooling. So instead of relying HN output, one idea could be like I'm going to do average pooling. So I'm going to take an average of all the hidden states, and that is going to be my features for my neural network to make the classification. Yeah, all that is possible. Yes. Question?
Continuing her question about generation or generative capability of RNN, sir, is this true generation? Because we are not sampling from a distribution as we do in case of, say, other generative models.
So what do you mean by true generation?
For example, we know that an autoencoder is not a generative model.
Yes.
Similarly, are we also not doing something similar with RNNs? We are not really sampling at each point, I would say, and then.
Right. So when we are training the model, we are basically just training the model to assign the highest possible probability on what actually came next. Now the model has a mechanism to assign probabilities for what could come next. Now you're using that probability distribution to generate outputs. You could either say that whatever that distribution recommends, I'm going to sample in that proportion, which is what is typically done. So these are generating models. These are called autoregressive generative models. This is like the G of GPT, right? Generative.
Does it work well for generation?
Yeah, this is not bad. The RNNs for language models are not bad. In fact, there is a post by Andre Karpathy which is dating back to 2015. It says the unreasonable effectiveness of RNNs. So you should check it out. He has a lot of interesting analysis. Yeah, these models are not terrible at all, even though they look very, very simple. They can generate much better output than 3 gram, 4 gram models.
So in that RNN for sequence classification, is it so do we train them separately or do we
No, it's all. So the question is for sequence classification, is this RNN part and the feed forward network part trained differently? The answer is no. They're all trained together.
So like if I have one sequence where there are only 8 words about the review and another sequence where there are 50 words about the review, we are compressing everything to a same HN which will be having the same dimension. So it will become a bottleneck as the...
Yeah. So great question. So if the sequence length increases, like it may happen that H is no longer sufficient to encode, and the architecture is also maybe because of a lot of matrix multiplication is not capturing enough information. All those are valid concerns. These are concerns that transformers take care of. So we will come back to that, yes.
Can you reiterate the point on the advantage of RNN when you're saying like for sequence classification, you don't need to specifically choose the output dimension?
No, you do have to choose the output dimension. It is just that you don't, you have variable length sequence and it captures context. So compare this to bag of words. Bag of words did not capture ordering at all, right? Desert was good is same as good was desert, right? Here everything is fed sequentially left to right. There is a notion of second word, third word, fourth word and so on. So this is a improvement over that.
probably in the previous slide here. So the unit will predict hands if it is directly given. So what if we take long and hands as the not only the next word which is actual word, along with that what if we take the previous predicted word?
Okay, so you're saying rather than and, let's also take and plus one more word which is the predicted word.
No, you said that so predicted thanks. So
okay, let's say by mistake it predicted thanks, yes.
So I gave this thanks along with long.
Along with long, yes.
To the second unit.
Okay.
So now my embedding will have both the actual word and the
misclassified word, yes.
Misclassified word. What will happen then?
So one thing is that when you are initially training, you typically don't do that because these are very arbitrary. The model is not yet trained properly. So you will give the correct answers all the time. But let's say you have trained it to some degree and now the model is at least right 75% of the times. So in the 1/4 cases when the model still gives a wrong answer and you still input thanks, the expectation does not change. You still want the model to predict and, correct? So because you don't know what would have come next because somebody did not write so thanks something. What you saw in your data is so long and. So you will continue imagining or assuming as if the answer was right. Okay. So, okay, this is good. So there are a few other interesting things you can do with RNNs. One thing is like, as I was suggesting that we can stack up layers in feed-forward networks. Nobody is stopping you to add more layers on an RNN. So in an RNN2, you can have multiple layers where, let's say, the H1 here is the input to the first RNN in layer 2. Similarly, the output here is the input to the first RNN in third layer. Why are adding more layers important? Why were adding more layers in a feed-forward network important?
Capture more higher level features.
Yeah, great. So they can capture more abstract, higher level features rather than superficial, surfacial features. So the same intuition, same logic, same observation applies here. This is also a way to add more capacity to a model, add more free parameters, so that if your task is more complicated, those functions can also be learned.
What do we mean by that RNN are being?
So basically, like this RNN has a W and a U, right, which is common for this. But the second RNN will have a different W and a different U, which will be common across the second layer of RNN. Similarly, the third RNN layer will have a different W and a different U. So it is like saying that whatever output came of the second RNN is my input to a new RNN.
So we will have 3 edge generating from.
Correct. So you will have an edge generating from here and another edge here. Yeah.
So how will you compute loss into gradient descent?
So like maybe the simplest answer is we don't need to think about it because autodiff will do it for us, PyTorch will do it for us. But if you really want to think about it, like Y2 is a combination of this edge, right, which is a combination of this, and so basically all the weights associated with these affect Y2. So a loss that is incurred due to a misclassification at Y2 will update all these parameters.
From the block at the X1, so are the horizontal and vertical edges same or they are different?
They're different. So horizontal edges are also different because time steps are different. So if you insert third word, your H3 will be different because it now has seen the third word, right? Like think of just one layer neural network, your edge changes with time. Similarly, because the input to the second layer is outputs from the first layer, your edge will by default differ, right? Because you are seeing a different input. So all edges are different, both horizontally and vertically. Yeah. So this is maybe clear. RNNs can be stacked. Another interesting thing you can do is RNNs can be bidirectional. So even though we write left to right, some scripts are right to left, but there might be some signal that is important to capture from write tokens, right? So if you are, let's say, doing sequence tagging or labeling as it is called, where you have the entire sequence with you and you want to tell, let's say, the part of speech tag of every word, whether it's noun, verb, determiner, modifier, you have the entire sequence with you. In some of those applications, people have seen that it is helpful to run a forward RNN which moves left to right and a backward RNN which moves right to left. So how should you think about right to left RNNs? So think of it as a left to right RNNs operating on the reversed string, right? So like the first input to that RNN is the last word, second input to that RNN is the second last word. One second. And once you have two RNNs, the outputs at each time step can be combined. So let's say the output of the forward RNN after consuming x1 is h f of 1, whereas the output of the backward RNN after consuming everything, because this is the first word of the sequence, which means the last word of the bidirectional sequence, will be concatenated with h of backward n. And this could be like your output from a forward RNN and a backward RNN. If you want, you can stack multiple forward and backward RNNs also, right? So if you want to, let's say, do text classification here, right? If you want to do text classification here, it might help to have a context that is captured from right to left. Sometimes it's also better. Why? Because the left to right RNN sometimes can lose out information that it saw a long time ago, right? Similarly, the backward RNN can capture information for those things much better, right? Because it has seen those tokens at the last.
So does this completely solve the problem of that long?
No, it doesn't completely solve the problem, but it is like 1 to 2% better than just using a single unidirectional RNN.
For language modeling, we are not supposed to show the
Yeah,
next token.
yes. So bidirection, so the question is, for language modeling, we are not supposed to know the future tokens. Exactly. So bidirectional RNNs cannot be applied to the task of language modeling. It can only work if you have the entire sequence with you. In the task of language modeling, you only have the prefix and you're trying to predict the next word. So bidirectional RNNs cannot be applied to language models or the task of language modeling. Question, yeah.
So you said that in the case of certain languages which are left to right compared to right to left. So what if you reverse it during the prediction itself? So you reverse.
Yeah. So if you say that I'm going to use one RNN on the string that is as is and another RNN on a reverse string and combine the output, you have just invented a bidirectional RNN, right? That's exactly what it is.
But I am not going to wait for the output of that last output of this.
So basically, like in this case right here, I am only concatenating after the output is generated. So in some sense, bidirectional RNN is quite independent of the forward direction. Sorry, the backward RNN is quite independent of the forward RNN. Only their outputs are combined.
So this can be parallelized on the.
This can be parallelized, yes.
But how does the second RNN get the output? I mean, independently they get the output, or they have the output of the RNN1?
No. So the backward RNN does not have the output of the forward RNN. It is operating in the right to left direction. That's all. So if you look at this figure carefully, the xn goes to the backward RNN, RN2. Nothing from RNN1 goes to that, right?
The output is concatenated.
Only the output is clubbed and concatenated, yes.
But when the loss happens, you have to flow through.
Yeah. So the loss happens, it will flow through both. So whatever, let's say you combined the output and made a prediction, that was a bad prediction, all that will, yes. So both RNNs will be updated due to a loss. Okay, so I think we finished the RNN component, but remember that there are like two major weaknesses. What were they? Sequential and then longer contexts. Okay, so we'll fix that. Like transformers will improve on those capabilities. So let me go back to the transformer section, okay.